Today I choose to talk about something kind of related to our collaboration with METTLER TOLEDO in the use of PAT tools and instrumentation, and use of those PAT tools, but also some modeling tools in order to estimate parameters for salty knot crystallization. This work was done in the context of collaboration with Drexel University, and it was done by a very bright lots of experimental work was done with a very, very bright student, Anjali Patel, who currently is in Stanford University doing grad school. So a quick outline of my talk today. I will start with a background, problem statement, if you wish. Then I will talk briefly about how we did determine the concentration of the salt during the crystallization, which was not a trivial exercise at first. So we had some online PAT measurements, offline measurements, and also what method we used to determine the concentration of the salt. I will follow up with the parameter estimation. We do have a Matlab-based model that we use, but also we worked in collaboration with scale-up systems to build a template for salty knot crystallization. I will finish up with some results from the computation and simulation, and will conclude with some conclusions. So quickly a background. So we deal with a salt formation, which typically you see this very often in the pharmaceutical industry, where we have a parent and we add a counterion to it to make a salt. There is several drivers, several motivation to make a salt. It can be solubility enhancement or chemical stabilization and so on. So in this situation, we have a parent which is a free acid. We add a counterion in solution at constant temperature, and the salt will crystallize in this situation as elongated rods, and which is prone to breakage, and I'll get back to that later. So the objective here is to determine crystal growth kinetics and eventually breakage descriptors from the experimental data. We have two processes. They are essentially the same. What we call the particle forming step is the same. The chemistry prior to particle forming step is different in it. We went from process A, which had 5 stages, steps in other companies, to process B, where we cut down into 4. Several other advantages. We used safer reagents, and we actually limited the cost. So the objectives, as I mentioned earlier, determination of the crystal salt concentration from the FTIR, ATR measurement, but also the crystallization kinetic parameters, and we study the effect of these major parameters in the crystallization. So quickly, a description of the procedure, which has a reactor with free acid and alcoholic solvent. We dissolve it at elevated temperature, and then we add the counterion at elevated temperature. Here where the solid comes out, and then we cool with filter. Pretty simple salt formation. So we have identified three critical parameters, which is the tip speed, the agitation as a factor, the concentration of the counterion in solution that's being dosed between low and high, and also the addition time, or addition rate. We have 2 PAT, very popular, FBRM to essentially chord length, and counts, and FTIR, which gets peak area. We'll get to that. And we have some offline measurement also, where we use microscopy offline to determine the size in 2 dimensions. We use NMR to determine the concentration of the salt. And this is used to correlate the FTIR peak area to the root concentration. And as I said, the goal is to extract the crystallization kinetics and determine effect of parameters on product attributes. So this is experimental setup, very familiar, EasyMax. We have it connected with an FTR, ATR probe, but also an FBRM probe, just to get chord length and IR data. We did not use the dosing unit that comes with it, just because the counterion can be corrosive, so we had used other means to dose, like either syringe pump or peristaltic pump to dose the counterion. So how we do determine the external salt concentration? The problem here is like the parent and the salt, they vibrate in the same wavelength. They are essentially the same molecule. We just add a metal, And so they have the exact same signature in terms of IR. So how do we differentiate between the two? How do you extract the salt contribution to that IR signal? And so a few assumptions or few things that we do know. We know that mixing is, the blend is achieved very quickly. So we have good mixing in the EasyMax, the 100 ml reactor. Knowing that the IR is average over 60 seconds, we have an average of what's going on with this 60 seconds. So mixing is not an issue. And also, we know that the IR intensity at the end of counter-ion addition corresponds to the solubility. So we know we have that point. Also knowing that the salt solubility is very low, assuming that the Beer-Lambert rho is essentially we have a linear relationship between peak height and concentration. The assumption that we make is that the salt formation is instantaneous, meaning that from the moment the counter-ion hits the solution, it reacts with the available parent in there. So from these 3 or 4 bullet points, we determine the correlation between the IR signal and total concentration. Okay, so that's the total concentration, meaning the contribution of the parent and the contribution of the salt. And knowing that the salt is crystallizing, so essentially what's in solution that comes out here. And knowing the subtracting the salt that's forming, we can determine what's left in terms of parent. And then combining these 2 points, we can extract the concentration of the salt. So how does it look like in real life? We obtain the FTIR data. We extract the salt peak area by removing the contribution of the acid, and we correlate the peak area of the acid with the salt. Sorry. And from there, we can determine the correlation between we can determine the salt concentration of salt during the experiment. And essentially, this is how it looks like. We receive the contribution of all of them. The green is the contribution, essentially what we have from the drop. It's essentially the free acid and the salt dropping, and then when you extract the contribution of the acid, you have your salt increasing. At some point, the crystals come out. Here, at first, there is no change because there is no crystals. When the crystals start showing, the solute start dropping, and then you see there's a peak of concentration or peak of supersaturation, and it drops back to 0 at the end of the addition. So we monitor that with FBRM as well, with the G400, and we can see here the onset of nucleation, and essentially we can monitor what's going on with total counts and also the temperature. This is isothermal. At the end of the addition, we drop the temperature to isolation temperature, and we have the peak area as well as dropping during the crystallization. And then here, the change here we essentially due to the fact that we're decreasing the temperature, so the IR signal is also a function of temperature. And so this is just, we take essentially 3 samples to measure the size offline via microscopy. And you can essentially determine the size in 2 directions, as I said, and extract the aspect ratio each time. And this data will be fed into the models later. So the 2 growth mechanism model that we used is simplified model. It's work that's 40, 50 years old. We adapted it to the 2D growth in 2 direction, where the growth rate essentially is a function of the step propagation in both phases. Okay, and as you can see, the fast-growing phase is here is W. It grows faster because essentially it's a function of the step advance in the other phase. So essentially, what's happening is that this grows fast, meaning that DL on DT is high. I'm not going to linger on this, just move quickly. So we can determine the elementary or fundamental relationship for the width and length. They are interrelated just because the width depends on the step advance on the other phase and vice versa. And what we're interested in is essentially 2 what we call integration coefficients that we need to determine experimentally from the experimental measurement. So we did that already for an anti-solvent crystallization, where initially all the solute is essentially a reservoir solute, and then you add seeds and you start crystallizing, and then initially you have all the solute in there. When it comes to reactive crystallization, essentially you have at time 0 you have 0 salt molecules, and then they form as you add the counter-ion. So you adapt it to that nuance with the salt, with the reactive crystallization. So essentially the concentration in solution is the number of molecules in solution at time t minus what's already crystallized, which is obvious. And so we use that to determine the mass of the salt form at time t. As you can see, it's a function of the addition rate of the counter-ion solution and the initial volume. Going quickly, so we can determine the concentration, transient concentration, which is essentially a function of the size of the crystals, which is distribution at time t. So that we need to determine a solid integration method. So we have an objective function, which is to minimize this error, which is essentially the difference between what the model computes and the actual concentration of the salt. But also we look into the aspect ratio. So aspect ratio computed minus the one that's experimental. And we have only two measurements. Obviously, we have way more measurements online, so we need to weigh that so that the contribution of this error doesn't overweight the two measurements we make for the aspect ratio. So a few requirements: we want to have a high resolution estimation, we want to compute in minimal time, obviously, and also we want to find a global minimum of the error. And so what we found, we tried a few things and we found that this one works better. Essentially, we scan both KW and KL in a known range where they're supposed to be. And for each value of KW, we scan L from the initial value to X maximum value, which is KL cannot be higher than KW, obviously, because it's a lower growing low rate growing phase. And so we use a two-tier estimation. At first, we use low resolution, meaning the incrementation between the steps higher. We locate the region of the total global minimal of the error, and then we do another scan with a higher resolution on that region. I think I'm gonna just skip this real quick because this is essentially three nested loops where we set the value of KW, we set the value for KW, and then we scan for KL, and then go on, keep doing that until we cover the entire region. And this is how it looks like. So this is the low scan. We see the values here. Logarithmic scale are much larger. We locate where is the global minimum, and then we do another scan on this region with a much better resolution to locate the global minimum. Once we locate the global minimum, that will give us the value of KW and KL that we will use. So this is a template that's available on the Scale-Up System website. So we worked with our peers there to develop a template for the salt formation. And essentially the template extracts growth kinetics values expressed here by Kj, but also the order of the, so essentially it's an empirical expression for the growth rate. But also you have the possibility, it's versatile, you can add breakage kernels if you think that breakage is occurring. And so there's quick differences between the two approaches. So here it's an integration limited crystallization. It's first order. We're not considering breakage. It's a size-dependent growth, but also it's anisotropic growth. And one input we need is a salt concentration, from the FTIR. We have a two offline PSD measurement in two directions with a microscopy. The output is 2D growth parameters, KW, KL. Dynochem model is diffusion-based model. It has variable order. Can consider breakage, size-dependent growth, and as isotropic, it returns only one value for the growth rate. The input here is salt formation, salt concentration, but also FBR chord length, which is translated into moments. The output is growth and breakage parameters. So these are the results we got from the two approaches. As you can see, we found actually a similar value between the Dynochem growth model and the KW, which is the fast growing, essentially the higher value of K from our MATLAB algorithm. And so what this says is that in early stages, the breakage is not significant. I'll get to that later. But also the contribution of the sort of growing phases to the supersaturation depletion is low. But it's kind of counterintuitive that the growth kinetic from the Dynochem model, which is one dimension, is similar to KW. And so if you look at it, if you think of a BRM beam crossing a needle, statistically you'll see that it should cross the needle more often in this direction than in this direction. And so essentially what it returns should return the value for the low growing phase, because this one doesn't grow that fast. What we see is different. So how is that? What's the source of that observation? So if you look at it, if you have needles and you have streams, liquid streams going, if the stream is going in a radial direction, or an axial direction, I'm sorry, what we call it's a non-effective transport, meaning that the streams, they will go on the side of the needle and they don't push it. However, if the stream is going on the radial direction in this way, then transport is effective. So what happens, so what is the result of this? The result is that it happens to what we call stacking. And essentially, because the needles are pushed mostly in this direction, they will end up being stacked like that. And you look at it, envision it similarly to like hay stacking. You know, if you come from farming family like I do, this is very often the case. So it's very easy. You can stack hay using a rack, and it, you know, it's something very similar, we think, to what's happening with needles in solution, especially if you're in laminar or transitional flow. We end up having the cross beam, the beam of the EPI crossing in multiple directions, but what's going to happen mostly is going to reflect the chord length in you know, the chord length will be much higher than the width. It's going to rather be a function of the length than the width, and there may be a possible explanation with the high values you obtain with the FPR movements. And in situ with the PVM image, this is essentially what it looks like. You can see that taken image randomly, the needles are more stacked in this direction. Moving on quickly on the computation. So having extracted those values, we looked into how they compare with you know, what kind of computation we can get, and essentially looking at the effect parameters on supersaturation, or salt concentration. So the counterline, when we decrease the addition rate, the maximum supersaturation decreased, which is expected. And also we see that simulation experimental trend agree with the expectation. However, the simulated salt concentration diverge at larger values. And so we think that for fast addition, we have faster growth. So the growth rate overweight breakage, end up having better prediction of the model. However, at later stages, the needles are longer, they are more prone to breakage, and the breakage becomes more significant, so we have poor prediction of the model. We looked into the potency, the concentration of the sodium hydroxide in solution. When it increases, the maximum supersaturation increases, which is also an expectation. However, we see that the supersaturation is higher than experimental result at a longer duration. And essentially, what the effect of counterion solution potentially is similar to that of the addition rate. Just adding more counterion at any given time. So the higher concentration of the counterion, we have higher supersaturation. The higher supersaturation increases the growth rate. And then again, we find out growth rate overweights the crystal breakage in early stages, and then you have better prediction. However, at late stages, because the crystals are longer, they're more prone to breakage, we have like a drop of the, a faster drop of the supersaturation of a salt concentration, which results in a poor prediction of the model. It's because the model doesn't take into consideration breakage. So agitation speed, we did calculate the flow regime, which resulted in transitional flow. And that's one of the explanations also, because we still have streamlines. Maybe that's lead to the stacking of the needles in solution. And so we did look at the difference. This is just FTR data between two different agitation rate. The counterion addition added over 2 hours. As you can see, with a tip speed, a higher tip speed, initially we have more or less the same concentration, but as you can see at the higher tip speed, the concentration drops faster. And we do believe that that's because of, at certain time, the breakage start to become more important, especially for the higher speed. That's what leads to this, because you're generating more surface available for growth. So because of you have more breakage at higher tip speed, then you'll have faster depletion of the concentration and supersaturation. And similarly, with the salt concentration, you have 4 hours. You see this essentially a similar effect with a higher tip speed or higher agitation rate compared to the lower agitation rate at later stages. This is a quick comparison between the two routes. We did see that for route A, we have a lower aspect ratio than for route B. One thing to know is that the two routes have different impurity profiles, and just to highlight the fact that impurities can affect your growth into the environment can affect the growth. So impurities can have an effect, actually a dramatic effect on the aspect ratio. Just a number to highlight the difference, what leads to these needle-like crystals. You can see the difference. It's almost one order of magnitude in value between Kw and Kl. However, we do see a maximum concentration, similar maximum concentration for both routes. But we do see more elongated crystals, as I mentioned, with route A. Less elongated, I'm sorry. To conclude, we introduced a fairly straightforward method to extract salt concentration from a system where you have the salt and the parent have exhibiting the same IR, and that's from the FTR measurement. Also, we present an algorithm for salt concentration, for anisotropic growth. We successfully combined FBRM and FTIR to get good estimation of crystal growth and breakage parameters. We have evidence that breakage becomes significant as crystals grow larger, and that's reflected by the deviation of Matlab model, but also the concentration measured experimentally at different tip speeds. Both models return similar values for growth rate, and we give an explanation, possible explanation as to why the FBRM is returning the same value as the fast-growing phase. And finally, the estimated crystal growth parameters reflect the change in aspect ratio between the two chemical synthesis routes. Last but not least, I want to acknowledge a number of people, colleagues and peers who helped us do this. First, I want to acknowledge Anjali Patel. I mentioned she did the hands-on work on this in the lab. But also a number of my colleagues, but also our peers. Joe, Peter, and Andrew help us from Scale-Up Systems. Dominique, Des, also for their collaboration. And finally, I would like to thank you all for coming, attending this, this symposium. And I would like to take any feedback from you, try to attempt to answer any question you might have. Thank you.